Okay, everybody, today we are going to start or take our Lewis structure discussion to the next step. We are going to discuss multiple bonds and the Lewis structures for polyatomic ions because the rules for drawing those and multiple bonds are a little bit extra, so I wanted to talk about those with you. First, we're going to try to draw the structure for CO2. Now, we're going to draw it using the same rules that we've used so far. Carbon has 4 valence electrons, and there's one of them. Okay, and I know carbon has 4 valence electrons because it's in group 4A or 14 of the periodic table. Then we have oxygen with 6 valence electrons, and there are 2 of them. Remember, our first step is to count up the valence electrons. So in this case, my final structure will have 16 valence electrons. Next step is to draw the skeleton structure. Now, since carbon is in the front, it goes in the center. And the oxygens go on either side of it. Okay, because we want the molecule to be balanced. Next step is to connect the outer atoms to the inner atoms using a bond. Okay, and remember, a bond is a single pair of electrons. Sorry, it does that every time I circle. Okay. Now that has used up 4 valence electrons. So I have 12 left to account for. And I put my valence electrons on the outer atoms first. That's my next step. So 1, 2, 3, 4, 5, 6. I do that to complete the octet onto oxygen. Okay. Now, the other oxygen will look the exact same. Okay. Now, that accounts for 2, 4, 6, 8, 10, 12 valence electrons. Uh-oh. I am now out of valence electrons. Every valence electron has been accounted for, but you may notice that carbon does not have its octet. Okay, since it doesn't have its octet, it's not done yet. Okay, so let me erase a few things. So what happens, and I'm going to change the color of my pen real quick. What happens is one of the lone pairs from oxygen actually goes down here to form what is called a double bond. Okay, where we get carbon double bonded to oxygen. Oh, no, I don't need that one. So that now oxygen still has 8 valence electrons, but now carbon has more. Now carbon has 6 valence electrons. Okay? But we want one more pair. So another pair is going to go between carbon and oxygen, and it's going to share to form something that looks like this. So that oxygen still has 8. Each oxygen still has 8, but now carbon has 8 because it's sharing 2 pairs with each oxygen. And that is a double bond. A double bond shares 2 pairs of electrons. That way we can still satisfy the octet. And what happens is the inner element pulls in an extra pair from the outer elements. Now, there is a little bit of possible confusion here when it comes to carbon dioxide. We could technically form any one of these 3 structures because if we look here, oxygen has 8, oxygen has 8, and carbon has 8. But now we have what's called a triple bond. Well, now we have a triple bond where we're sharing 3 pairs. Then, of course, we have the one we just drew. But then there's another one as well. This is called resonance. Resonance occurs when there are multiple possible correct Lewis structures for a compound. So when there are multiple possible, oh wait, that doesn't need a comma there. Correct Lewis structures. Now, we're not going to draw resonance structures because there are a couple of rules that go to drawing resonance structures that we're not going to talk about. But I wanted to talk about the fact that they exist. And we know they are we know that each of these are correct because all the atoms involved have their octets. So if we find a structure that has multiple correct Lewis structures, that means the molecule is capable of something called resonance. Okay? Now, let's go ahead and try another one. We're going to draw the Lewis structure for hydrogen cyanide or cyanoic acid, I think. Cyanic acid? Hydrogen cyanide. Whichever. Okay, so hydrogen, since it's in the first column, has 1 valence electron. There's only 1 of them. Carbon, of course, has 4 valence electrons. That's something you should probably commit to memory. It's equal to 4. And nitrogen has 5 because it's in group 5A or column 15. But there's only 1 of those. So 5, 5, 10. So our final structure will have 10 valence electrons. Now, drawing this one seems a little tricky because I've always said that the first element goes in the center, but hydrogen never goes in the center. Or better yet, never goes between atoms. So hydrogen never goes between atoms, so it can't be in the middle, which means the next one in line goes in the middle, which is carbon. So we draw our skeleton structure, we put everything on the outside. We connect with bonds. That accounts for 4 valence electrons. So I have 6 left. Now I complete the octet on the outer elements. Now, hydrogen doesn't need an octet. Remember, hydrogen only has a duet. It only has 2. And since it's already sharing 1 pair with carbon, it is fine. So, we go and we look at nitrogen. Nitrogen only has 2 valence electrons right now because it's only sharing 1 pair. So, it gets 6 more valence electrons to complete its octet. Unfortunately, that eats up all of my valence electrons, and I don't have any left over for carbon. Carbon doesn't have an octet. Now, if you think back to carbon dioxide, when our center atom didn't have an octet, we reached over to the nearest element and grabbed a lone pair to form a multiple bond. So now we have a double bond. But carbon still doesn't have an octet. I don't have any valence electrons left over. So carbon is going to reach over to nitrogen and grab another one. Okay. Oops. to form a triple bond. Okay? A triple bond is 3 shared pairs. Okay? So a triple bond is 3 shared pairs of electrons. 2 originally, and then, or 2 electrons that have been pulled over by the bond, and 2 more pairs that have been pulled in to form the multiple triple bond. Okay? Now, let's talk about polyatomic ions. This is the cyanide ion. It is polyatomic. It is polyatomic for a couple of reasons. We call it a polyatomic ion for a couple of reasons. 1, it's made up of more than 1 atom. And 2, it has a charge. It has a 1- charge. So, when we draw the Lewis structure, we still account for the valence electrons from the atoms. But since it has a -1 charge, that means it gets an extra electron. Okay? That's from the -1 charge, or the 1- charge. Okay? There's only one of them. So our final structure will have 10 valence electrons. So, since there are just 2 elements, we put them in a row, or we put them side by side. We connect with a bond. Now that takes up 2 valence electrons, and I have 8 left over. So I'm going to put them on the outer atoms. Remember, we always start with the outer atoms to complete their octet. So I'm going to go ahead and fill in the octet on nitrogen because it needs 6 more. And that accounts for 6 valence electrons, so I have 2 left that I'm going to put on carbon. Problem is, carbon doesn't have an octet. Right now it only has 4 valence electrons. So when the inner element doesn't have enough valence electrons, and I don't have any valence electrons left over, I pull a pair in to form a multiple bond. Carbon now has 6, nitrogen still has 8. Unfortunately, carbon doesn't have enough, so I pull in another pair to form a multiple bond. Now carbon has 8, now nitrogen has 8. But because this is a polyatomic ion, I put it in brackets, and I put the charge in the upper right-hand corner. So polyatomic ions require brackets and charges. Okay? And that's one thing that makes them stand out as different. Remember, when we have an extra charge like we do up here, okay, we need to remember that we add that to our total number of valence electrons. Okay? Now we're going to draw another polyatomic ion. We're going to draw the structure for NO2-. Nitrogen has 5 valence electrons, and there's only one of them. Oxygen has 6 valence electrons, but there are 2 of them. Plus I have a -1 charge, so I have a free-floating electron, and I have 1 of them. So my final structure has 18 valence electrons. Now, in order to draw this, I put the front atom in the center, and I put the other ones on the outside. I connect the outer atoms to the inner atoms with a single pair of electrons. Okay, and that accounts for 4. So now I complete the octet on my outer elements. Okay, since oxygen already has 2 from the shared pair, it only needs 6 more. And the other oxygen's the same way. That accounts for 12 of the valence electrons, and I have 2 left over. Any leftover electrons always go on the center atom, and that eats up the rest of my electrons. But I'm not done yet because nitrogen still doesn't have an octet. If the center element doesn't have an octet and I don't have any valence electrons left over, we form a multiple bond. So I pick one of the oxygens, it doesn't matter which one, and I take one of its lone pairs away, and I create a double bond. Now, nitrogen has 8, oxygen has 8, and the other oxygen has 8. But since this is an ion, I'm not done yet. I have to put it in brackets and put its charge in the top to the top right. Now I'm done. Now here's the rub. I told you we weren't going to draw resonance structures, and we're not, but I just want to show you. Here's another possibility. If you drew it like this, then that's okay. Since we have multiple correct structures, we say it has a resonance structure. Okay, and what that means is basically the real-life molecule is switching back and forth between those 2 structures. Okay. Now there is a couple more things I want to talk about. First are, let's talk about boron trifluoride. Boron trifluoride looks a little weird. Okay, if we were to draw it out the same way we've been drawing everything, it would look like this. Okay. Oh, it would help if I wrote the number correctly. Okay. My outer atoms are connected to my inner atom. I complete the octet. Okay. That's what it would look like. And this is actually the correct structure, even though boron doesn't have an octet. Boron is an exception to the octet rule. Boron only holds 6 electrons. So this is actually the correct Lewis structure without a multiple bond. And I just wanted you to know that because this shows up on like, if you take chemistry in college because you want to be a nurse or something like that, this always shows up on tests. Because every professor in the world thinks it's like a trick. Okay. Boron only holds 6. It is an exception to the octet rule. It has what is called a diminished octet. Okay. Now, here is one that's weird. There are no correct Lewis structures for NO2. Now, we just did NO2 minus. This is just NO2. And here's the reason why. N has 5 valence electrons, and there's 1 of them. Oxygen has 6 valence electrons, and there's 2 of them. So we have 17 valence electrons that need to find a home. We organize it, okay, the same way we organize the other one. But here's the rub. I've got 2, 4, 6, 2, 4, 6, 8, 2, 4, 6, 8. So that's 16, 17. Okay. Now, no matter what I do, I cannot complete the octet here because I have an odd number electron. This is called a radical. Radicals are lone electrons that don't have a pair. Okay, so they are unpaired electrons. And they are very, very, very reactive. Antioxidants take charge of free radicals because when there is a free radical present in the body, it can cause a lot of damage because they're very reactive with just about everything. So antioxidants are kind of like drawn to free radicals in our body and kind of take them in a safe and helpful way. So that is how you draw more advanced Lewis structures with multiple bonds. That's how you draw Lewis structures for polyatomic ions. And then there are a couple of the exceptions for Lewis structures and things like that. If you have any questions, feel free to leave a comment below or shoot me an email and we will talk about it and get it worked out.